This slide demonstrates you mechanism of electrolytic dissociation of ionic compounds and ion dipole mechanism. You see interaction between salt crystal, sodium chloride, and water molecules, and in solutions, you see the changing for cation and anion, this forming hydration shells around chloride, anion, and the hydration shells too around sodium. And this orientation, the dipole of water, orienting towards the ions of the crystal lattice of sodium chloride, the water molecules form hydrogen bonds with them. I hope you remember about type of bonds, hydrogen bonds. A large amount of energy is released, which is called the energy of hydration. You see, dipole-dipole mechanism. One type of mechanisms of electrolytic dissociation. Mechanism of electrolytic dissociation of polar compounds, a dipole-dipole mechanism. Under the influence of dipoles of water, we see that dipoles of water oriented to this dipole, our substance. The polarized covalent bond is converted to see our substance, for example, hydrogen fluoride. Polarized covalent bond is converted into an ionic molecule, and the hydrogen fluoride molecule decomposes into two hydrated ions. You see the hydrated cation, hydrogen cation, and hydrated ions anion, fluoride anion, hydrated. Concentrations of ions in solutions of weak electrolytes are qualitatively characterized by the degree and the dissociation constant. Degree of dissociation alpha, we will use Greek letter alpha to mark degree of dissociation. So degree of dissociation alpha is the ratio of the number of molecules that split into ions and to the total number of dissolved molecules, N. Alpha is equal to ratio. In numerator, you see N, and in denominator, you see the number of dissolved molecules and big letter N. The isotonic coefficient associated with the degree of the electrolytic dissociation. You see that one variance of this formula, that isotonic coefficient is equal to 1 plus alpha multiply K minus 1, or in other mathematical variants after transformation, alpha is equal to isotonic coefficient minus 1 divided by K minus 1, where K is the number of ions which results from the decomposition of one molecule of the substance. The degree of electrolytic dissociation is expressed as a percentage of in fractions. A dynamic equilibrium is being established with the time between non-dissociated molecules and ions of weak electrolytes. You see on this slide example for weak electrolyte, ammonia solution, ammonia hydroxide. You see, I hope you remember about this symbol, two-way arrow as marker of reversible process. For weak electrolyte, you see the association to cation and anion and constant constant equilibrium that is equal to, please remember about constant from Maslow, is equal to ratio between product concentration for product and the initial reagents. In our case, initial concentration of ammonia hydroxide, where K, this index E, equilibrium is the equilibrium constant, which corresponds to the dissociation of weak electrolyte. The magnitude of the constant depends on the nature of an electrolyte and a solvent temperature, but doesn't depend on the concentration. You see, equilibrium concentration for calculating doesn't depend on concentration, but depends on nature and the nature of an electrolyte and a solvent.